Good morning, everybody. So our next speaker used to be a paraglider pilot, now spends his time rock climbing, and has a personal best of 45 seconds solving a Rubik's Cube. That's about 2 months faster than mine. On top of all that, he's in love with functional programming. Please welcome Esteban Marin with his talk, Learn Physics with Functional Programming.
Thank you, everyone, for coming. Well, my name is Esteban Marin, and I'm very happy to be here at LambdaConf. I want to share with you a beautiful experience I had thanks to functional programming. So why are we here? Have fun learning physics with functional programming and communicating through types. So this talk is about objects and arrows that points to those objects, and you will see a lot of that throughout the talk. Last year, I learned that functional programming is a great tool to learn physics because functional programming is a great way to write math. And physics is expressed in the language of math. And the relationship between math and programming is now more present than ever. Therefore, applying my everyday debugging software engineering skills, I was able to get a deep understanding of physics while writing code, and I had a lot of fun doing that, and that's exactly what I want to share with you. In this talk, I hope to explore Newton's second law, describing the problem through types, writing math as code to help us compute functions, and I believe this is a new perspective of learning physics and functional programming. So, why functional programming? Functional programming lets us think about the complexity of physics through the lens of objects and arrows. Function programming uses mathematical notation that allows us to describe the problem clearly and precisely. Furthermore, you will see throughout the talk how our understanding of physics evolves just by writing names to objects or magically implementing the code while mapping the mathematical function into Haskell. Functional programming has a simple mathematical basis that supports equational reasoning, and equational reasoning is an awesome tool. Throughout the talk, I will interchangeably show you code, math notation, types, and function plotting to describe the same object and use equational reasoning to show physics from several angles. Finally, why Haskell? So Haskell is an awesome tool to draw objects and arrows. People do not see this as a graphical language, but I would like to show you otherwise. Taking a math equation and transcribing it letter by letter into Haskell code, we will see how our implementation will derive magically. But another thing is that we will get types for free. And this is really mind-bending for me. So let's start first describing our domain problem through types. And over here, we just write in types in Haskell. And we start with the wrapper of real numbers over a double. And I know this is a big assumption, but we will just carry on. We will also see what a typical function definition is, which is a real number that takes a real number. And I want you to picture in your head like the typical math function you would write in a piece of paper. And there are three functions that we're interested in studying, which is a position function, a velocity function, and an acceleration function. Now, visually speaking, how does this look like? Visually speaking, the compiler is representing the following. Everything's encoded in a real number, acceleration, velocity, position, and time. And the real interesting question is, how do you jump in between the endpoints? How do you go from a position function to a velocity function and move? And even more interesting, how do you come back? And the answer is arrows. And arrows in Haskell is a function. So describing the problem in types, we can start implementing the code. So if you see, this is the first question that we want to answer is how do we jump from a position function to a velocity function and from a velocity function to an acceleration function. So mathematically speaking, what we want to do is define velocity as the distance traveled through time, rewriting the definition for small t's, and then limiting that to limiting the delta t to 0, we will arrive to the definition of an instantaneous velocity. So implementing this in Haskell, the code in Haskell is a one-to-one mapping of the function you would write on a piece of paper. And this could also be Python code too. However, the real kick is when we start studying this through types. So as you see, the type derivative is a higher order function. It takes a function and returns a function. And honestly, I never thought of derivatives as higher order functions, but there you go. Higher order functions help us glue nicely the code, and it will contribute us to build a very complex model at the end of the talk. Now that we have the definition of a derivative function, let's revisit our question. So the real question is, how from position and time measurements can we infer the velocity or the acceleration of a particle? That's the real question. And the Haskell implementation is very straightforward and very ergonomic using a point-free notation. If you see, velocity from position is just the derivative, and we use the function we just did. And moving from velocity to acceleration, we use also the derivative function. So visually speaking, how does this look like? The derivative gives us the ability to move clockwise in the model. And this is very powerful. But how, as I told you, how can we reverse this movement? Like going counterclockwise, or like what's an antiderivative? So before answering what an antiderivative is, I want to explore another idea that came before derivatives, which is dividing something into parts and then add them all together to get an approximation of the whole. And here we're stating that the area is the bounded integral of fx between a and b. But I'm gonna show you a trick is that I'm gonna move to the left the unbounded integral and to the right the area. And the intuition that I want to present you here is I want you to think what's to the left side of the equal sign as the mathematical object that we want to arrive or that we want to represent, and to the right as how we're gonna get there. Think about it more as the right side of the computation, or what we're going to give to the computer in order for us to calculate a bounded integral. So let's see how calculating an area in Haskell looks like. First, we start with the sum of all rectangles of height f at t times a small delta t. So if you see, that's the definition of a rectangle. And then there, we will need a stream of rectangles that go after that. And using the midpoint rule here, that's how we're going to calculate that integral. The final Haskell code looks like this. And it's pretty much the rectangle area and then just t at a stream of a midpoint using the midpoint rule. I do believe this is a very precise way of communicating the idea of an integral. And also, we get a goodie is that we have now types for this function. So let's see what the types of this looks like. So if you can see, we can solve integrals either analytically, or like we did in high school or in college, or numerically. What we want to do now is just explore numerical integrations, and more precisely, we want to give the Haskell, we want the computer to perform all of these integrations so we can explore our model even further. On top of that, I want to show you that an integral takes time and performs a numerical integration, and a numerical integration is something that takes a function, two bounds, a lower and upper bound, and then returns a real number as a result. So at this point, I want to come back to how do we move clockwise and counterclockwise in our model. And for this, I will let these geniuses enter the stage, and we will take their work for face value for now. But what Newton states here is that derivatives and unbounded integrals are just part of the same. One is just the inverse of the other. What does that mean? So mathematically, the fundamental theory of calculus is presented as such. The bounded integrals from a to b equals the antiderivative at b minus the antiderivative of a. So revisiting the intuition of moving terms around to the right side of the equal and to the left side of the equal, we want to arrive to this function. We want a way to calculate the antiderivative of any function. So how can we do this in Haskell? Moving the terms around, we see that f of x, it's the antiderivative at point B plus the bounded integral of the function that we're studying. And I'm showing you below how the Haskell code looks like, and it's pretty much we're building up top of what we already have, an initial value f0 plus the integral of the function. Again, let's look at the types that we get for free. If you see, the type of the antiderivative is, surprise, surprise, a higher order function. It takes a function and returns a function. And we will delegate that computation to the computer so we can get a numerical answer in real time. This means, therefore, if we have a velocity function and we integrate it, we will get a position function. So antiderivatives allows us to commute between functions like derivative did, but in the opposite way. So in this case, we can go from a velocity function to a position function, and from an acceleration function to a velocity function, just by doing the antiderivative. So this is a point-free style, and it doesn't feel like code, but again, this is just usable Haskell code. So now we have a very cute model in Haskell that can solve any kinematic high school physics problem. And recapping, everything's encoded as a real number, acceleration, velocity, and position, and we can go back and forth using derivatives and antiderivatives. So now let's play around with this. And imagine we go outside and we start letting fall several objects, measuring their position, their time, and their mass, which leads us to this parabolic that we're used to, this parabolic function that we used to see. So can we make predictions about having this curve? Can we make predictions about the velocity and the acceleration? And the question is yes. For the parabola, when we derivate a parabola, we will get a slope. And if this is moving clockwise. And if we derivate that parabola, we will get a constant. So I would like to picture yourselves doing this experiment for several months, varying the mass of the object and arriving to the same acceleration constant. This is another moment of Newton's brilliancy because he noticed that this constant acceleration is part of a bigger picture. So Newton claims, the force is proportional to the mass times the acceleration. And I'm presenting the acceleration as a second derivative because I want to imply there's a differential equation that we want to solve. So this is our new model, and we have this new we have this new object, and we want to see how it connects with our other relationships. So Newton created a scientific method by dissecting problems into really small chunks and then compose those methods to create a really complex model. We will start with a version of the problem that asking how does it behave when the force is constant. So for example, a falling apple. So Newton states that the force is inversely proportional to the mass of an object. So for this force problem, the force is seen through the acceleration, and from there, it's going to stimulate our model. And moving from the acceleration, we do the antiderivative of the acceleration, and we will start seeing the velocity function we saw previously. And then if we continue going counterclockwise and we antiderivative this function, we will get a parabola, and this is consistent with what we got into our lab. So this is definitely a useful model. So let's get a little bit more creative and use our model to make predictions of velocity when we're modeling a cyclist, for example. So this is a step function, and what we're trying to describe here is this like 10 newtons when we pedal, and then coasting again, and then 10 newtons when we pedal, and then we coast it again. So it's a fairly complex model, and a slope should appear in the velocity gauge and will increase from the description of forces. So this model is still fairly basic. So let's see how can we explore more connections of the model, like a direct arrow from force to velocity, and what does it take to get there, and what can we learn? So this arrow describes the air resistance problem. It's normally avoided in intro physics class because it requires to solve a differential equation. However, we're gonna tackle it head on because it's gonna give us the ability to solve differential equations, and we can build the model up there. So let's go to the whiteboard. I'm gonna coast a little bit here because it's a little bit complex, but this is Newton's second law rewritten in the form of the derivative of velocity. And this is the Haskell implementation. As you saw, it's very concise and precise. And the types are very interesting because we will start from a description. The velocity will be a descriptor of the state of the model, and we will have a list of functions, an initial velocity and an next velocity. How are we going to solve this integral? So this differential equation. We're going to use the Euler method. And visually, the method takes an initial value. It calculates the slope using the next value as an approximation. And obviously, with each step, the approximation gets worse. So at the end, the Euler method reduces the solution to the velocity at delta t plus the velocity at t plus delta t. It would be an initial velocity plus the derivative of velocity times time. This is called the initial value problem, and write it in Haskell. It's pretty straightforward because we already built on those functions. So let's explore the types. So the types that it gives us there is that we're taking time, mass, a list of functions that describes the system, a current velocity, and then we will get a velocity. Okay, so visually in our model, we have this now new arrow that goes into velocity function, and I want to stimulate this model using the step function I presented you earlier. So what predictions can we make about this? Like, how would the velocity function would look like? So by playing around with the area and drag constant, one solution could look like this when the cyclist reaches terminal velocity, or the other one is when pedaling headwind. So you would see how the velocity increases, and then we will see a seesaw function. Now, as you can see, this is a pretty cool model. It solves a differential equation, but can we improve it? And the answer is yes, we can. Now, we're not going to encode over rational numbers, but we're going to encode over vector and vector spaces. How would this look like in Haskell? I'm going to get a little faster, but we have an x, y component, and this is all the operations that we are used to with rational numbers, but we have it in Haskell. What does it mean? Like, this is a derivative and antiderivative, and using vectors, you can barely notice the difference in the implementation. So pretty much, our intuition commutes. And what we would like to abstract now is we want to have like a black box Newton's second law solver that takes a list, a description of the state, a particle initial state, and then we will have a position and a velocity function. The intuition here is that we're starting from a description of the state and the particle using the data types we describe below, and we introduce a new type, which is a one-body force. And I know you know the one-body force, two-body force, three-body force problem. So this is a one-body force problem that takes a particle state and returns a vector, and we will inject that into this Newton's second law solver to have a position function. So what's a particle state? A particle state will contain all of the information that we want from the system, like mass, charge, time, position, and velocity. And this contains everything that we really care about. So I want to show you a constant force mass problem, and we're going to see how our model behaves, what are the predictions that our model is going to do with this. So if you see, we're going to take So right now I'm just gonna type types in this part because it's better to explain it as like this is the part where I explain physics through types. So you will see that in order to get a position function, we will take a numerical method that could be the Euler method that I just described, or the Runge Kutta 2, and we take a particle state, a delta particle state, a one-body force, an initial value, and then we will get that position function. So scrambling around a little bit more through the types, I want to show you how we're going to study the problem from the Newton side, the Newton prediction, and from the relativistic point of view. So if you see we have a one-body force description of the problem, we're going to take a differential equation that's going to be the same in both cases, and then we're just going to solve it. And if you see here, the interesting thing is we are using for both models the same differential equation solver. And here, if you see the Newtonian wave, it's predicting that it's not only that it's not capping at the speed of velocity, but it's even increasing, and it's going past that. And here, the relativistic has an asymptote at c. So pretty much, we went through 500 years of math and physics in less than 20 minutes. But we were able to take this ride because functional programming is a great way to write math. And math is a great tool to handle complexity and to describe nature. I hope this inspires developers to explore the side of code that is about using math, functions, differential equations, and math objects rather than blindly going for the next upcoming framework. Being able to explore nature through mathematical models, using differential equations, and making useful predictions through computers is a skill of the future for software engineers. Thank you.